Good morning, ladies and gentlemen. So, we have reached the final topic of the year for AP Physics 1. We've gone through various types of motion, how we get things moving, how we get things to wave up and down, and how we power light bulbs. And finally, we've gotten to the very last piece, which is rotating motion, and the very last topic, rotational motion, which is referred to as angular momentum. Now, angular momentum, we're going to find out, is very important, especially as you start to go farther out into the universe. And it's very important for a lot of things in the universe in terms of stability. So, we're going to start, though, by simplifying. We're going to start by remembering a time when all we ever did in the classroom was just throw balls at different people. All right, of course, those were great times, very exciting. What were two things that happened when you experienced that collision? And I know you can't really answer it, but hopefully you said something to your computer screen along the lines of, oh, well, we experienced pain and we experienced the oomph of the collision. And we're going to talk about the idea that that pain is just kinetic energy. It's kind of how we describe it. And the oomph was the idea that it represented the momentum of the collision, the tendency of an object to want to keep moving forward. All right. And the more oomph, the more momentum that object has. Now, for linear momentum, we have, of course, a formula for that. And remember that that formula is just linear momentum is just equal to the mass of the object times its linear velocity. And we talked a little bit about what happens when you have collisions, explosions, and the idea that an object that's moving has momentum. And now we want to talk a little bit about what it looks like when it's not about an object that's just moving forward, but now it's about an object that is rotating. So what I want you to do is I want you to grab a coin, preferably a penny or larger. If you try it with a dime, it's going to be pretty dang difficult, but if you want to go hard mode, you're welcome to. Now, I want you to try and balance it on its edge. Now, once you've done that, and it'll take a couple tries probably, once you've done that, I want you to see if it's easy to knock that penny over or whatever coin you use. And more than likely when you do this, you are going to find out that it is remarkably easy to knock that thing over. Now, once you've gotten it bounced on your edge, what I want you to do is I actually want you to roll the coin. Get some sort of small little poking stick, whether that's a toothpick, whatever it is that you can poke the coin with, because what you're going to do is you're going to basically make the coin roll, and then you're going to kind of push it on its side, and you're going to see, and don't like whack it, but kind of push it, see if you can knock the penny over as easily as you could before. All right. Now, I haven't tried this demonstration, so I assume it'll work, but try around with that. Once you've kind of gone through the demonstration, you can start the video again. So pause the video, then restart it once you've done this, and we'll talk about hopefully what you saw. All right, so hopefully, after you had a chance to kind of play around with this, you probably saw that something interesting happened once you rolled the coin. So it's really easy to knock the penny over. It was just sitting there on its edge. But as it starts to roll, you might have noticed that if you're not pushing it too hard, you actually can kind of make it tilt a little bit, but it won't fall over. It's going to keep moving forward. All right? And we're going to find out is that what you have done is you have given that coin what we refer to as angular momentum. It wants to spin. And what's interesting about angular momentum is that when you cause something to spin, it wants to spin in that exact setup, exactly the way you set up. And another way to see that is I want you to click on this link to this video, because actually this is going to do a very good job of kind of showing what's going on. So I want you to click on this link to this video. And I will also click onto the link. Okay. Now, I'm not going to watch the whole thing because I'm not particularly interested. I don't want to have to watch the whole thing. But if I click this, what's going to happen is this individual has a bike wheel. And we have one in the classroom. Unfortunately, I can't use it. But basically, what it starts with is it's hanging like this. Okay, it's hanging vertically. Now, they're going to cause the bike wheel to start to spin. And what happens is we're going to set it up so that the bike wheel is now going to be sitting like normal. And you can see right here as we kind of watch it. So the bike wheel is now spinning. As you could probably see earlier, if I thought this is normal, I just took this bike wheel and held it and set it up like this, not spinning, more than likely what's going to happen is the wheel's literally just going to fall down. And it might start swinging back and forth, and oh my gosh, you might have created a pendulum. But by giving this bike wheel some spin or some angular momentum, when you set it up, instead of it falling, it actually wants to keep spinning in that exact same orientation. And what happens is that now it basically stays up. It stays stable. Now, the reason it's spinning has to do with something called precession. It's not particularly relevant to this class right now, But basically, the reason it's spinning, just in case you're interested, is because the rope is actually providing a torque on this bike wheel, because it actually wants to rotate kind of around that center point. So it's providing a torque. The bike wheel wants to kind of keep moving in a kind of moving forward or moving in a straight line. And what happens is these two things kind of combine into making some sort of circle. All right. And of course, if you go into higher level math or higher level physics, you'll talk about precession in much more detail. All I really care about is the fact that the spin makes it so that that bike wheel does not want to fall down. All right. Now, because of that, all these things lead into our definition for angular momentum. All right. And what that is basically just like an object that is moving forward wants to keep moving. An object that is spinning wants to keep spinning in that exact same setup. So angular momentum is basically the tendency of a spinning object to want to keep spinning in its exact orientation. Right? That means that if I had a top and I cause a top to spin, that top wants to keep spinning exactly the way that you threw it on the ground. So, angular momentum is just the tendency of a spinning object to want to keep spinning in its exact orientation. For our formula, what we're going to do is just like we did for linear momentum. Oh my gosh, we're going to translate it. So, linear momentum was just equal to the mass times the velocity. So, angular momentum is going to be dependent on the rotational version of mass, which remember is the moment of inertia, times the rotational version of velocity, which is angular velocity. All right. And what that looks like in formula form, for reasons that probably in Latin or Greek make sense, but not in English, angular momentum is represented with a capital L. So angular momentum is equal to the moment of inertia times the angular velocity, which remember is an omega, but because I don't feel like trying to write up that omega, it's just a W. Now, there's also one other way you can calculate angular momentum, and this one can seem strange at first. We're going to practice with it. It's for the angular momentum for an object that's actually going around something. So this would be useful for something that maybe is orbiting, or something that runs into an object and causes it to start spinning. So the angular momentum for a point object is equal to the mass of that object that's moving in a straight line times its velocity times basically the distance away it is from the turning point. And we're going to practice this, I promise, because right now it doesn't seem like it makes much sense. We're going to practice a question a little bit later on that shows how to use that. So right there, angular momentum is really just dependent on the moment of inertia of an object times how fast it's spinning. And what we're going to find out is that objects that when angular momentum starts to kind of drop on a spinning object, it actually causes some weird things to happen. So looking at this next question, all spinning objects have angular momentum. As angular momentum decreases, what starts to occur? Unfortunately, we can't do any demonstrations in here that show that, but what you'll start to see is that when an object starts to lose angular momentum, it starts to wobble. All right, its motion actually becomes less stable. So the object begins to wobble, and it starts to slow down as well. And we'd say it spins slower. All right. Because what we're going to find out is that angular momentum is the main reason for doing a lot of different actions in civilization where we cause something to spin. And that actually leads very nicely into our example question. How does throwing a spiral in a football, rifling in a gun barrel, and spinning a top all utilize angular momentum? So take a second or two, just kind of pause the video. Think about how everything we just talked about, how angular momentum might be useful for those things. And then once you're ready, come back and we'll talk about it. All right. So hopefully you had a chance to kind of think about those various things. The uniting factor in all three of those ideas is that they are all encouraging spin in the object. And what that does is it actually makes these things much more stable. So spiraling a football, rifling a gun barrel, spinning a top, all they do is give it some angular momentum, which means that those objects are not going to wobble in the path they've chosen. So if you spiral a football, it means that where you're throwing that football is going to be much more accurate because the football is going to go in a consistent path. Just like rifling in a gun barrel makes sure that the rifle bullet is now spinning, so it has much more stability in its flight. And spinning a top, when you spin a top, it makes sure that the top doesn't just topple over as soon as you put it on the ground. So in all cases, we can say all three of these objects gain angular momentum, which gives them stability in their actions. They won't wobble. Okay, and I do apologize. I know these are all, angular momentum is something that's really useful to observe, and unfortunately we just don't have any observations that we can do in this question, but there are a ton of things that you can easily do just by looking it up online. Now, the last piece of angular momentum that's rather interesting is the idea that just like linear momentum, angular momentum is conserved. And what that looks like is, what I want you to do is I actually want you to pause this video and I want you to watch the figure skater demo, because it's going to show what happens. And I want you to pay attention to what happens to the figure skater's spinning velocity as she starts to bring her arms closer together. So pause this video, watch that, then come back and we'll talk about conservation of angular momentum. Okay, so hopefully you get a chance to kind of go through and watch that. That figure skater video is rather fascinating because it shows perfectly the idea of how angular momentum has to be conserved. So what happens is, just like linear momentum, an object that has angular momentum has to keep that same amount of angular momentum regardless of what's going on. But angular momentum is dependent on two things. It's dependent on its moment of inertia, and it's dependent on its angular velocity, which means that the starting angular momentum, or excuse me, this has to equal the final one, which means the starting, whatever happens with the starting angular velocity and moment of inertia, kind of has to affect what happens at the end of all this. All right, and I apologize, these are really ugly. This should be IF, WF. Now, what that means is just the fact that looking at this, if you change either how fast something's spinning or its moment of inertia, it's going to affect the final part of what happens. And in this case, what's happening is, as our figure skater is bringing her arms in, she's causing the moment of inertia to decrease. And because of that, according to the law of conservation of angular momentum, her spinning velocity has to increase in order to keep angular momentum consistent. So what's happening is that when you kind of do that with your arms, and that's anything that you have in your house that you can spin with. If you have a spinny chair, you can do this. If you're on a spinny chair and you start with your arms wide out and you bring them in, you're going to start to spin faster. It's because that system has to obey the idea that angular momentum has to stay the same. So in order to adjust for the fact that moment of inertia change, the spinning velocity has to change as well. All right. Now, all that kind of changes into just this very simple formula right here, where the law of conservation of angular momentum looks just like this. And basically, conservation of angular momentum, the angular momentum I start with has to equal the angular momentum I end with. Now, one last thing we can do is you can actually, before we go to the next video, is that angular momentum actually also relates back to the idea of impulse. And just to kind of bring that back, we can just look at it and say, impulse, remember, is what caused a change in momentum. I guess the best way to describe it is maybe angular impulse. I don't think it really has a fancy name. But basically, for this, impulse and angular momentum, what we saw originally is that impulse was the mass times the change in velocity, which would be equal to the force times the change in time. Okay, remember, you had to apply force over some time to cause a change in momentum. Well, for angular impulse, all you have to do is that the change in angular momentum, all right, let's say delta L, it's just going to be equal to whatever torque you apply times the time you apply for. Now, we're not going to really practice using this, and we're not going to use this torque formula much, but it's just something that you've seen it. Because sometimes I just like to bring up these formulas so that you've been exposed to them, so that if you run onto them later on in life, you know what's going on. So, with that being said, ladies and gentlemen, that is kind of the first explanation about what angular momentum is. The second video is going to be focusing on the practice questions in the second half of this, where we're going to practice using angular momentum. So with that being said, ladies and gentlemen, you can head to the next video, and I will see you there.